Okay, let's get started. Okay. So for the rest of the notebook, I think it's quite straightforward. Okay, right? So you make a model, and this is for training data, right? So we do a prediction for training data, and then get the predicted probability, and then with the predicted probability and with a threshold, we can then calculate the confusion metric, right? And with the confusion metric and with the definition of this traditional metrics, we can easily use the confusion metric to calculate the accuracy, sensibility, and specificity, right? Okay. But this traditional metric has a problem, right? Because it changes with threshold. So nowadays we would like to use this AUC, which is a metric that consider the capability that the model can discern, can distinguish the two different classes, right? Okay. So the AUC is the value between 0.5 to 1. Okay. So the closer the AUC is close to 1, then basically if we have AUC better than 0.8, then you have a very good model already. Okay. So it means that in all of the threshold, after considering all of the threshold, the ability that the model can distinguish the two different classes. And that is basically the purpose that we want to build the model, right? We want the model to tell us, right, to distinguish the two types of people, right? That is the main purpose, right? So AUC is actually the a better accuracy metrics. Okay, so here in the in this notebook, this is actually just I just put in the formula in R, right? So I define the model. I define a function call, so we can evaluate. So given the confusion metrics, we can evaluate these three metrics. And this is for testing data, right? If we want to predict the testing data, then we need to specify the new data when we calling predict, right? Okay. And so this time, this is the distribution of predicted variable for testing data. Okay, right? And again, if we can do the confusion metrics the same way, right? So and then you can actually compare the accuracy, sensibility, and specificity for training and testing data, right? Okay, so by using this as apply, okay. But as I mentioned, in order to do this confusion metrics, you basically need to actually when you want to calculate this accuracy metrics and confusion metrics, you don't really need to plot you don't really need to do the plot, right? Because this plot is only for to get you a better idea about how to do it, right? So after you do the prediction, if you want to see the confusion metric, you simply just make this function call, right? Okay. So simply put, in order to build model, we do a function call. In order to do prediction, we call predict, right? And in order to do the confusion metric, you basically just use this function code. And all of the code that used to, this plotting is actually just to give you a better idea about what we are doing, right? Okay. So basically, if you only want to see this matrix, you basically just make a few function call. And again, this is the distribution of predicted probability. Okay. So in two class, right? In two class, and here I left some exercise so you can actually do the plot. Actually, you can reuse this code. Just change this here to testing, and here is predict 2, right? Okay, so, because for testing data, we actually put the prediction in predict 2, isn't it? Right? And the true value is actually in TS. Okay, right? And this predict equal to predict 2. Then you can make the same chart very easily. Okay? And here are some concept about the ROC and AUC, right? So I already give you some example. You can use the simulator to see how the sensibility and specificity change when the threshold is moving, right? So, but actually, if you want to draw the ROC curve and actually get the AUC number, it's also very simple. You don't really need to understand the detail. If you only want to like draw the ROC curve and calculate the area under curve, you simply call this COL-AUC function, right? And for training data, this is the predicted probability, right? And this is the true Y value, okay? Okay, and this argument specifies whether you want to make the plot or not. If you false, then it would simply return the AUC value to you. Okay? So if you specify that's true, then in addition to returning the AUC value, you also make a plot for you. Okay? So, well, practically, it's actually very straightforward. When you want to build model, you call GRM. When you want to do predict, you call predict. Right? When you want to do the confusion matrix, you simply make a table, right? And just specify the actual value and the prediction value. And here, you need to specify the threshold, right? Isn't it? Right? So this is to make the confusion metric. And to calculate AUC, again, it's just one function code. Okay? And all of this chart, all of this graph is just for your better understanding. You don't really need to do that when you actually use this logistic model, right? So in R, everything is already prepared for you, right? It's one simple function call for making model, one simple function call for making prediction, okay? And in order to do the confusion matrix, you simply call this table function that we have used a lot of time already, right? And given the actual value and actually the predicting probability with the threshold specified, then you get the confusion metric, okay? And if you want to draw the ROC curve and actually calculate the area under the curve, then you simply call this function, okay? And up to this point of time, I'm using a model with only two prediction variable. But actually, in this data set, we have a lot of data variable, right? So this model ID is not useful because it's just the member ID, right? So as an exercise, I ask you to build a model, right? To build a model with all of the predicting variable. I think use all of the column except member ID to build a model that predict pool care. Okay? Okay, and basically you just repeat all of the code. But when you are building model, you are using pool care. And here, on the left-hand side of the this tilde, you actually just put in all of the predictive variable except the member ID. Okay, and you can. This is your. I left for your assignment, right? So you simply follow the code here, okay, and do basically the same thing, except that you are using all of this variable except member ID to build the model. Then you will see that the accuracy will actually be better. Okay? Okay? So this is basically what we want to talk about, the logistic regression. Is there any question up to this point of time? No question, right? Okay. So now let's go to up to this point we are use data to build model, use model to do prediction, and we also try to evaluate the accuracy of the model, right? Okay. So this is what we cover up to this point of time. But actually, the reason that we want to build a model is not to do the prediction, right? We want to do a decision, okay? We want to let the model help us do the decision, okay? So that is the purpose of business analytics, okay? So in order to do a decision, let's think about in the business context. If you are the insurance company, okay, if you are the insurance company, and you build a model and you have a prediction, okay, so what can you do with this prediction? Okay, that is much more important than the prediction itself. Is decision, right? If someone is poor care, right, and if someone has a very high probability of poor care, then I might want to do some intervention, right? I may send some people to visit the patient, right? I may like give him some special treatment, right? But all of this treatment, all of this extra treatment would cost money, okay? So if I give the treatment to all of the patient, then it will be waste. There will be a lot of waste, okay? But however, in the other hand, if I do not take any action at all, then the poor care person will have a very high risk, right, of complication, and he would incur a very high cost of medication, of Medicare, isn't it, right? So for an insurance company, you need to determine where is the cut-off threshold that I want to do the treatment, okay? So the decision is kind of like the model was already give you the distribution, right? Given the model and given the data, you actually can have this distribution. But only this distribution cannot determine the confusion metric, because you also need a cutoff, right, before you can do a prediction metric, isn't it? Right? Okay. So after the model gives us this predicted probability, we need to determine the cutoff threshold. Okay. So above the threshold, we will do the treatment. We will take action. Okay. And below the threshold, we do not take action. Okay. But the question is, where is the threshold? Where is the optimal threshold? That is the thing that we want to determine in the rest of the class today. You get it? You get it? Okay. So we have model, and the model can give you this prediction probability, distributed prediction probability. But we need to determine the cutoff threshold so that we will have a maximum expected payoff, right? When we are doing decision in business, we are always looking for the optimum or maximum expected payoff, right? So the optimum decision is the cutoff threshold that would incur the maximum expected payoff. But how to calculate this expected payoff, right? We have a confusion metric. After we have the confusion metrics, we also need to have a kind of payoff matrix. Okay. Let's take a look at the practical meaning of each cell of this confusion metric. Okay. So in this context, if the patient is actually 0, and we are now when we are making decision, this is not negative or positive. We are talking about action or no action, right? Positive, we want to take action, and this is no action. Okay. So in this cell, it is actually good care, right? And we do not take action, right? Okay. So good care, no action. Then in our context, based on our experience, we can say that they do not have the risk of diabetic complication, and we do not take action at all, right? So the net payoff is 0, right? Because all is well, right? And we do not take action, okay? And in this case, if they are good care and we take an action, okay, then there will be a cost, right? Okay? If these people, they are good care, but we take action, then the cost of action, you will need to pay for the cost of action, okay? And of course, the number here depends on what the action is, right? And you basically can do an assumption, or if you already have this action experience in applying this action, then you will in history know its cost, right? So here is that it's good care. You don't really need to take action, but you take the action. So for each of this case, you would like spend some cost of action, right? Now let's take a look at this case of I think here could be better. Okay, so let's take a think about the case of poor care, right? So it's actually what for these people. So this guy, he is for the number here, for the patient here, he is actually poor care, and we take no action, okay? Because they are poor care and you do not take any action, so they have a high risk of diabetic complication and a high risk of insurance costs. The insurance company will need to pay a lot of like Medicare costs, isn't it? Right? Okay. So this is the cost of risk, as we can say that, right? Because you take no action, right? There's no prevention action, and you just let it happen, okay? So you will have a high risk cost, okay? Right? And in this case, if they are poor care and you actually take an action, okay? Of course, the action cannot like eliminate all of the risk entirely, right? It would eliminate some of the risk, but not all of them, right? Okay. So, for example, if you can reduce the number of risk from -100 to -50, okay, then because they reduce the cost of risk from 100 to 50, and you also have action cost, right? Because right now you are taking the action. So in this cell, it's actually the reduced cost of risk plus the action cost, right? So this metric, we call it payoff metric, okay? And the number within this payoff metric is based on your operational experience of the insurance company, right? You are an insurance company, so you know that if I do not take any action on these poor care people, in average, each people will cost me how much, okay? And you will have some action, and the action will incur some cost, okay? But if you make that action to the people who is a poor care, it can help to reduce the cost of risk, okay? Right? In this case, it reduced the cost of risk from minus, because it's cost, right? So we are talking about, so we use the minus, right? Cost is the minus payoff, right? So if you poor care and you take action, then you can reduce the risk of complication from the cost of complication from -100 to -50. But because you take action, right? So this -10 need to act into this -50, so it can become -60. You get the idea? This question? Okay. So the number here can be just assumption, or it can come from your operational experience, right? Now, if you because we already have a confusion matrix, right? Okay, after we set the threshold, we will have the confusion matrix, and if you time the number, right? The number of TN number to the corresponding average payoff, right? Okay, so if you time this cell to this cell, this cell to this cell, this cell to this cell, and this cell to this cell, and then we kind of like add them together, right? Okay, so we time Tn by 0, Fp by -10, Fn by -100, Tp by -60, and then we add the number. Is actually the expected payoff, right? Isn't it? Right? After you determine the threshold, you got a confusion metric, okay? And this payoff metric, you already make assumption there, right? Okay? And now combine these two metrics, you can calculate your expected payoff, okay? But we still do not know which cutoff is the best cutoff, right? Okay, so but since we can do our programming, we actually can change the threshold from 0 to 1, right? And when we change the threshold from 0 to 1, this confusion metric will change with it, right? And the expected value will also change, okay? So we can simply like scan all of the possibility value of cutoff to get the maximum, the maximum cutoff, which would produce the maximum expected payoff. Okay? So this is what we are going to do. It's kind of abstract, but in notebook 11B, we would like do it in the real data. Okay. So this is notebook 11B. Let's go back to RStudio. And then we open 11B, and also it's now execute the first chunk and the second code chunk. This is basically the same code that we already covered in 11A, so I don't need to explain. We make model, right? We split the data, we build model, we take a summary of the model, and then here is to kind of like again draw the distribution of predicted probability, right? With this DPP, actually we can put a threshold, and then we will get a confusion measure, right? Okay, so but practically you don't really need to draw this plot. This is only to make you understand it better, right? Okay, so so we can go back to this scheme and see how we can find out the best decision, right? Find out the optimal cutoff, which would lead to the maximum expected payoff. Okay, so first of all, we need to define the payoff matrix, right? Okay, so as I say that Tn in our context is like no action and good care, and this is nothing, right? So if we no action, poor care, then the average risk of poor care is very high, right? Okay, so this is action with good care. Then you waste the cost of preventive, actually I should say, preventive action, okay? You can make the change yourself, okay? The cost of preventive action, right? And the FP is actually FR, which is the cost of prevention action, plus the reduced risk after taking the action, right? As I explained it here. In this cell, they are poor care, and we take action. And this action would actually reduce the cost of risk from 100 to 50. But we also, because we take action, we need to add the action cost to it, right? So, so in this cell, we actually have the cost of prevention action plus the reduced risk after taking action. Okay, so now suppose that we already know this value, right? Okay, So it's 0 minus 100. And this is the way to define maybe let's do it here. It's easier. This is the way to define a metric in R. Okay, you put in the value and told them that it's a two row and two column 2 by 2 metric. Okay, so for cleanliness, I also specify the row name and column name, right? Okay, so this defines the pair of object, and now after you do that, you will see right, pair metric here. Okay, you'll see a pair metric here. Okay, so now you have the pair of metrics, and you also have the prediction value here, right? Okay, and you have the actual y value, right? This is the predicted value, right? And this is the actual y value. Okay, and so now we can start to do some simulation. Okay, we want to simulate the situation that the cutoff value change from 0 to 1, right? If you take a look at this, sequence, it actually is a sequence from 0, 0.1, 0.2 up to 1.0, right? So when we do the simulation, we simply scan all of the possible cutoff value, right? Starting from 0 to 1, okay? And then we want to see the expected result, right? And as I told you, the expected result is actually just the product of these two metrics and sum them together, right? So it's actually, if you know the confusion metric and you know the payoff metric we already defined here, right? Here, right? This is the payoff metric we already defined here, and confusion metric we need to do a table, right? According to every cutoff, right? The S apply and plus a function. It means that I want to apply this function for each value in the cutoff, and cutoff is actually a vector of from 0 to 1, right? Okay. So for every cutoff, we want to calculate the corresponding confusion metric, right? Okay. Here has a little complication, right? Usually when we do the confusion metric, we only need to like do something like this, right? Usually when we do the confusion metric, we simply do a table of y equal to 1 and actually predicted value larger than p. That's good enough, right? For the regular case. But here I actually put I transfer the things and these things into a factor. Okay, that is to make sure that the confusion metric is a 2 by 2 matrix. Okay, because sometimes when your predictive value is very low, right? For example, if I has a predictive value of 0.01, then the result would not be a 2 by 2 metric. Okay, so and that would cause trouble when you do the product of these two metrics. Okay, so in order to avoid this, I actually transfer y equal to 1 into factor, and I transfer this expression into vector. So if I do this, here it was still be a 2x2 matrix. Okay. Yeah, as you can see that it was still be a 2x2 matrix. So the thing is like it is actually very easy to like in R to like do a simulation for all of the cutoff value and implement this kind of like decision schema. Okay. It's simply just if you know how to write R program, it's just like this, simply this, like this 4 lines of code. Okay. First of all, you actually have the vector of cutoff, right? And then this is what we call simulation, right? Because we want to simulate the confusion metric corresponding to each of the cutoff, right? So when we do the S apply of this cutoff vector, then it would, for each of this cutoff value, we basically will execute these 2 lines of code, right? Okay. And the first line is to generate the 2x2 confusion metric, okay? And the second line is the code that like do a product of these 2 metrics and sum them up, right? So as you can see, that's very concise, right? So after I execute this line of code and this line of code, I will have a result. Vector, and if I take a result vector, I will see that corresponding to each of this cutoff value, okay, corresponding to each of this cutoff value, this is the associated, this is the corresponding expected payoff, right? Okay. Of course, looking into so many numbers quite difficult. So the rest of the code, I make it a line plot. Okay, I just make a line plot, and within a line plot, I also label the maximum. The maximum result value, I mark it as a red point. Okay, here I do the calculation and mark the red point. So you know the for all of the threshold, okay, for all of the threshold from 0 to 1, for all of this cutoff, I see a corresponding result. So the optimum expected result actually appear at the cutoff of 0.16, and the value of expected payoff is -2360. Okay, this code is just simply just plot this is the cutoff value, right? And this is the corresponding expected result. So I simply put the cutoff value here and the expected value in the y-axis. Then you can see a curve. See? And in this curve, it's very easy to find out the maximum, and which is also indicate the optimum threshold, right? So what it means, what it really means is that with the model prediction, okay, if we want to take action, and if the action cost is 10, right, and the risk of cost is like 100, right, and the action can, when you apply to the poor care people, it can actually reduce the risk of complication from the cost of computation from -100 to -50, right? Okay. So with that assumption, we do a simulation, right? Because every one of this cutoff would lead to different confusion metric, and each of these different confusion metric will lead to different expected payoff, right? So after we do the simulation, we plot the result, then it will help us find out the optimum cutoff value, which means that if you are an insurance company, and if you take action, okay, on those patients whose predict probability is higher than 0.16, you will have a maximum expected payoff of -2360. Oh, it's minus because it's cost, right? These things are cost, so it's minus. But if you don't take action, okay, if at this point, if you set the threshold as 0.1, then every point is no action, isn't it? Right? So if you do not take any action, then you can see that the value could be like 3,300, right? 3,300, okay? And if you take the action, it actually can reduce the risk from 3,300 down to 2,300. Okay? That's the benefit, right? The business analysis would bring to your company. Okay? You get the point? Okay? So in order to do that, you don't really need to draw a lot of like DPP plot, that type of plot. Okay. Actually, all of this accuracy metric is not important when you are doing the decision. What's really important when you are making decision is the confusion metric itself. Okay. Let's go back to the basic. When we are doing decision, actually that accuracy, sensibility, AUC type of thing is like our concern. Okay. That metric is when you are building a model, you want to build a model with better AUC, right? That type of metric is used to choose a better model, to build a better model. Okay? And when you are really doing decision, you actually only need to know the confusion metrics. Okay? And in order to know the confusion metric, you need two information. The first information is the predicted probability, right? And you can acquire it by calling predict. Okay? And the second thing is you need to have a threshold, right? And with that threshold and predicted probability, you can build this confusion matrix. And with your payoff metric, which should be a knowledge, right? Experience knowledge of your company, right? Then you can calculate the expected payoff, right? And with R, we can do a simulation that scanned the cutoff probability from 0 to 1. And when we scan that cutoff value from 0 to 1, we will find for each of the cutoff, we will find we can calculate the expected payoff for the and then from all of this expected payoff, we can choose the optimum strategy, which is the optimum cutoff threshold that would lead to the best payoff, expected payoff. Okay. So this is the way that we do it, right? As you can see that this this line is kind of choppy, right? This is because we only have 131 data point, right? So here I do some I create more data, right? As I say that after we build the model, we want to like after we build the model, we want to like put in the entire population to get the to make their to predict all of the poor care probability for all of the patient, right? And the number of this could be very large, right? Okay, so I simulate a data set and call it the A data set, okay? And in this data set, I will have I have a number of 10,000 people, right? So if I, as you can see that Y now equal to A poor care. Now A has 10,000 patient, right? So again, I use A to do the predict. I will have a predict probability of like for each of this 1,000. Sorry, 10,000 10,000 people, okay, patient, okay, and then we can. This is basically the same code, except that right now the Y is actually A's poor care, and the rest of code is actually exactly the same, right? So you can see that when we have more, when you have a reasonable numbers of customer, right? The curve with kind of like smooth, it's kind of like smooth curve, right? So this is the way that we do the by doing simulation, how we can like the basic logic is here, right? Okay, you do the prediction, you get the probability, and then you have the cutoff to get the confusion matrix. Then you need to know the payoff. In your business context, you need to know this. This is your business domain knowledge, right? So combine your domain knowledge with the model prediction, you can calculate the expected payoff. The only open thing left is we do not know which cutoff is the best. So we kind of like scan all of the possible value of cutoff to get the best decision. Okay? Question? It's clear, right? It's clear. Okay, so let's take a 10 minutes break, and later on we'll have more practice. It's not over yet. Okay, we can do more sophisticated analysis and business analytics as we will see in the next hour. Okay.